Alrighty. Yeah, like one assumption. No, don't do that one. All right. So number 9, a Rutherford constructed model of the atom based on the results of the alpha particles. Rutherford constructed a model. Describe this model, right? Well, the model is just the picture, right? We've got the nucleus, the very, very small positively charged nucleus on the order of 10 to the minus 15th, right? And then I can't even draw it, right? But the electron orbiting a nice circular orbit. It's just like the solar system. Picture the solar system, right? Only the sun's a lot smaller, okay? And then the atom is roughly 10 to the minus 10th meters, right? There it is, right? Bohr modified the Rutherford model by introducing this condition, right? Okay. Outline the reason for this modification. I kind of didn't get all these marks, and I'm kind of salty about that. Basically, Bohr knew that what was going on was that the orbitals were quantized, and for some reason, when they were in those orbitals, they were called them stationary states, right? Okay, and in these stationary states, it wouldn't radiate radiation. Okay, whereas ordinarily an electron going in a nice circular orbit, sometimes the electron's here and sometimes it's not. Sometimes it's over there, right? Well, this is exactly how you radiate energy, right? So this Bohr atom should radiate energy, yet and an atom that's radiating energy can't be stable, right? So atoms would all be unstable. The electrons would spiral into the nucleus and be the end of the universe as we know it. So what Bohr stated just ad hoc just said, look, if they satisfy this requirement, they will not radiate energy. Okay, but I mean, the reason he modified it was that they were seeing these spectral lines. Right, so he knew the answer in the back of the book. He knew that when the electrons made transitions between the orbitals, that is, when they fell to a lower orbital, they would give off photons, right? So, I mean, that's the real reason. But that wasn't in the mark scheme, so I didn't get very many points for that, and I'm kind of mad about that. All right, let's go to the next page. The next page is going to go a lot better for me. Okay, so what's kind of cool is that you can actually derive the radius of the hydrogen atom using high school physics here, right? So show that the speed, well, if it's in orbit, right, let's imagine we've got this guy here and we've got a electron going in an orbit like that, right? Okay, well, we can just say that the Coulomb force, the K Q1, Q2 over R squared, right, is equal to the centripetal force needed for it to go in its nice little circular orbit, that it's either going in or not going in, or it's in a stationary state or not in a stationary state, and all that stuff, right? Okay, so this is the mass of this thing, right? K is K. This charge would be the electron charge of the nucleus. This would be the electron charge. So there's your E squared, right? Mass of the electron. Just solve that for V. V is equal to, yep. Okay, so take this expression and solve it. So this is Coulomb force equals centripetal force, right? Okay, use the answer in B and Ci to deduce the radius of the electron's orbit. Okay, well, so one of them is that MVR, right, is equal to N Planck's constant over 2 pi, right? Okay, so they're saying the ground state, right? So that's 1. Put a 1 in there, right? And then for the velocity, just plug this guy in. Okay. And notice you've got an R in the denominator and an R there, right? What I did, as soon as I plugged in the 1, and that's a 1. Okay, as soon as you plug in the 1 and plug in this for that, what I did was I squared both sides and then just did maths, and you'll end up with this, right? So do some algebra. There it is. So they love to do questions like that where you got to do a little algebra, right? Calculate the electron's orbital radius in C double I, right? Well, Planck's constant, look that up in joule seconds, right? In your data packet, K is 8.99 times 10 to the 9th. Mass of the electrons in your data packet, that's the electron charge, right? Just look up all those constants, plug it in, And you'll get about 5.3 times 10 to the minus 11th meters, right? And that's the radius, which means that what? The diameter is about 1.6 times 10 to the 10th meters, right? Which is what we think this is, right? On the order of 10 to the minus 10th meters. All right. Let's turn the page here. Turning the page. He's turning the page. All right. Rhodium 106. Rhodium. Decays into palladium. How come you don't capitalize palladium? I feel like you should. By beta minus decay. The diagram shows some of the nuclear energy levels of rhodium, and these are nuclear energy levels, not like atomic things, right? These are MEVs, right? Okay, and palladium 106. The arrow represents the beta decay. Okay, so let's see. Explain what must be deduced about the energy of the electron. Well, remember that it's going to go rhodium, right? It's going to beta decay to the daughter nucleus, right, which is palladium, which is still 106, right? Okay, and then since we're doing a beta minus, this guy becomes more positive, right? So it's a 46. So it's like one of these neutrons turned into a proton, right? And then we're also going to give off that beta minus, which is just an electron, right? And then to balance leptonness, we're going to give off an anti-electron neutrino, right? Okay. And so the energy of this decay, the total energy of the decay, is going to be the difference between 3.54 and 0.48, right? So the change in energy is going to be 3.54 minus 0.48, right? So state that, right? Okay, but a neutrino is emitted that carries off some of that energy, right? And so the energy of that electron is going to be somewhere between 0 and whatever this is, right? Okay, what is it, 3.06 or something like that. And in fact, when you look at these energies, it's like, here's Ke, right? And here's the intensity, right? It goes, and then there's this basically, this is 3.06 MeV is the cutoff, and it's got this little tail like that. So very, very few of those beta minuses actually have that energy, vanishingly small. It approaches 0, right? Okay, so that's what might be deduced, right? Suggests why the beta minus decay is followed by the emission of a gamma ray photon. Well, because it puts, this is palladium, and this is one energy level of that nucleus. Here's the ground state. Okay, so it's going to make a transition like that and give off a gamma ray, right? That represents the energy level, energy difference of that, right? So it leaves it in an excited state, right? Calculate the wavelength of the gamma ray photon. Just do this, right? Lambda is hc over E. And I went ahead and used the 1.24 times 10 to the minus 6 electron volt meters for hc. And I got something on times 10 to the minus 12th meters. All right, is that it for this? Oh no, yet there's more pages here. Let's go on to the next page. Okay, ooh, we get to complete the Fineman diagram, right? Notice that time is going this way, right? So if you emit a electron, you're going to balance that by emitting a neutrino, right? Notice that I got this wrong because I had the neutrino going backwards and, like that, like, whoa. Okay, but it's going to be like that, right? Now, this neutrino has to be an anti-electron neutrino, so therefore it's antimatter. Remember that antimatter goes backwards in time, right? And then identify that particle. Well, it's either W minus, W plus, or xenon, right? So if it's uncharged, and this is charged, right? If it's a positive charge on that branch, then it would be this. But you would do this guy because it's a negative, right? Okay. Draw an arrow to complete the Fineman diagram, right? So it's going to be the anti-electron neutrino, and it's going to be going backwards in time. All right.